Hello. So today I want to talk about wait, why am I all the way down? I don't know, I fell down there. There we go. That's better. That's better. Okay, so today I want to talk about the mean value theorem. It's another existence theorem in calculus 1. If you notice, right, it doesn't really give you a formula for the C that it's promising here, right? But it tells you that something exists. It's a promise that something exists. So in particular, what's our setup? We have a f is a differentiable function on a closed interval. Note the similarity there. We had a continuous function on a closed interval, right? So recall that continuous function on a closed interval, that is the basis for both the extreme value theorem and the intermediate value theorem, right? This is now a stronger precondition. We're now working with a differentiable function on a closed interval, right? So, and differentiability implies continuity, right? So any context where the mean value theorem holds, automatically both the intermediate and extreme value theorems will also hold. So we don't directly need this fact to talk about the mean value theorem, but it's just worth placing it in context. How does it relate to these other theorems that we meet in calculus 1, right? So so once again, we have a differentiable function on a closed interval, AB. Then we're told there exists a C such that f prime of C equals what? F of B minus f of A over B minus A. What is this? This is the change in Y over the change in X on that interval, on AB, right? This is f of B and f of A, they represent the y coordinates of our function on that interval, and A and B represent the x coordinates of the function on that interval. So this is what that represents, right? One nice way to think of this is if you think of this quantity here as the as an instantaneous rate of change, you can think of, or slope of a tangent line, right? That's a great way to think of that. So this represents the slope of a tangent line at some point x equals c, right? What does this quantity represent? This represents the average rate of change on that interval, right? The average rate of change on AB, right? Or you can also think of it as the slope of the secant line to the graph, right? Or the slope of the line connecting the endpoints, right? A comma f of A to B comma f of B, right? It's the slope of that line. So it's not a tangent line really. It could be by coincidence, but it's really, we're picking two separate points, A comma f of A and B comma f of B, and calculating that tangent line, right? So to see this in a graph briefly, what do we have? We have our function, some sort of graph, f of x, right? And then I have some point A. Here's A comma, the point A comma f of A on our graph. And then we have some point B, right? This would be my point B comma f of B. And what this is saying is that if you take those 2 points and you calculate the slope, right, between those 2 points. So this blue line has what as its slope? The slope of that line equals the change in y coordinates divided by the change in x coordinates, right? Rise over run. Good old rise over run. So that's the blue slope we're dealing with here. Now, what it's saying is that there will be some point C where we have a tangent line. So maybe here, the way I have this drawn, maybe that's the point C, right? I'm just sort of eyeballing it. where the tangent line to the graph of f at c would have slope what? Well, f prime of c, right? So this line would have the same slope. They would be equal, right? The slope of the green line, the slope of the tangent line at c. And we have a name for slope of the tangent line at c, f prime of c, right? So it's saying that if you pick your favorite interval on the graph, and on that interval it's differentiable, the function is differentiable, then the blue line, right, which is the line connecting those points, the blue line will have its slope matched by some green line, some tangent line on that interval, on the interior of that interval. So it doesn't give you a formula for that c, but it promises that such a c will exist. Let's look at this in an example, right? So let's ask, does the mean value theorem apply to the function f of x equals, let's say, sine, good old sine, on the interval minus pi over 2 to pi over 2, right? So ask, does this apply? And if so, find the promised c value, right? So that number that will exist on the corresponding open interval, can we find it if MVT does in fact apply? So let's think about this request here. Yes, this MVT does apply. And why does MVT apply? Well, think of the graph of sine of x. Right, here's f of x equals sine of x. And what do I have? I have x equals negative pi over 2, right? That gives me 1 point on our graph, and I have x equals pi over 2. That gives me another point on the graph. So this is pi over 2 comma 1 is the point we're looking at up there. And down here I have negative pi over 2 comma negative 1, right? So that's our a and our b, is that interval. So yes, it applies because sine of x is continuous and in fact differentiable everywhere, right? So in particular, it's differentiable on the interval, the closed interval minus pi over 2 to pi over 2, right? So yes, this function is differentiable everywhere, right? We have no vertical tangents, we have no corners or cusps, right? None of the things that make functions fail to be differentiable. We don't have that happening here. So what I want to look for now is I want to look for the slope, the c that we are promised, right? So in particular, there is the line that we're talking about, the blue line whose slope represents the average rate of change, right? So this has slope what? The blue line will have slope equal to f of pi over 2 minus f of negative pi over 2 over pi over 2 minus negative pi over 2. Right? So what does this become? This becomes, in the numerator, I have 1 minus negative 1. And in the denominator, I have pi over 2 plus pi over 2 is just pi, right? The double negative cancels. So then I get half a pi plus half a pi. So this ends up being 2 over pi, right? That's my slope of the function, my average rate of change of that function on that interval. Now, I can ask when is, for what c, right? For what c in this corresponding open interval, right? Open interval minus pi over 2 to pi over 2. For what c in that interval would f prime of c equal this slope, right? We just found this slope. Well, the mean value theorem doesn't give us a general formula for that, but even though the theorem doesn't, in a particular case like this where we have f of x equals sine of x, well, we know how to take the derivative of sine of x. We know how to do that, right? The derivative of sine of x is cosine of x. So now I have an equation to solve. So I have cosine of c, right? Just plug that c into f prime, right? And what would we get here? We'd get c would be arc cosine of 2 over pi. Kind of a strange value, but there we go. There's a c, right? And if you want, you can even get a decimal approximation for this, right? So this, say in Calc 2, maybe you would do this by a power series approximation, right? But if you want for now, you could just type it into a calculator and get a decimal approximation, right? So if we type in arc cosine of 2 over pi, one thing to notice is that this is actually in the domain of arc cosine, right? The range of cosine is only -1 to 1. So you're only allowed to plug into arc cosine numbers between -1 and 1. Fortunately, so note, 2 over pi is less than 1 because pi is a little bit bigger than 3. So this is a number kind of close to 2/3, right? It's a little smaller than 2/3, right? Probably 0.6 something, right? So it is in the domain of arc cosine. So it's a valid number to feed to an arc cosine function. And here, if you crunch it out, so let's say on a calculator, you get something like 0.88, right? This is the value that you get. Make sure if you type this into a calculator, make sure you type it in, make sure it's in radian mode. Right, it's definitely 0.88 radians, not 0.88 degrees. That would give you this this value from arc cosine, right? One way to think of that is 0.88 degrees here would make no sense because 0.88 degrees is, almost 0 as an angle, right? And if you take cosine of that angle, you basically get 1, or something extremely close to 1, not something close to 2/3, right? 2 over pi is close to 2/3. So that's how you know this is a radian value and not a degree value. So just something worth looking at and commenting on as you're doing a calculation like this. So, but yeah, so in radians we get 0.88. So where would 0.88 be? Well, that would be this value on our graph, something like right here, x equals 0.88, right? Because, and where, how do I know where to place that? Well, pi is about 3.14, right? So pi over 2 is about 1.5 something, right? So it's actually close to pi over 4. It's actually, it's before pi over 2 by a substantial bit, right? So that would be where we would have right there, we'd have a point, and at that point, the slope would be exactly equal, right? The slope of that tangent line would be exactly equal to 2 over pi, right? So this would have slope 2 over pi. That would be the slope, right? Now, one thing you can see here that's kind of interesting is just graphically, you could probably guess there is another solution to this, right? There's more than one valid C value. That's fine, right? The mean value theorem just says that such a C will exist. It doesn't say that only one C can exist. There could be more, right? There could be multiple. There could be 2 C's or 3 C's or probably many C's, right? This is perfectly fine, depending on the interval, right? So this is our, here there is another C value, and by symmetry you can see that this would be negative 0.88, right? Would be the other C value. It's just the mirror symmetry through the both the X and Y axis, right? The whole picture is symmetric. The whole picture lands back on itself if you reflect it through the X axis and then through the Y axis. If you do those two reflections, it becomes the same diagram. Therefore, right, that negative 0.88 must also be a solution to this. So those are there, right? Moral of the story is there are actually two values, right? Which the first one we got by calculating, the second one we got from the graph. So we have C could be plus or minus, right, arc cosine of 2 over pi, right, which is roughly plus or minus 0.88 radians. Right. So that's our C that is promised by the mean value theorem. And in fact, here there are two. Mean value theorem promised only one, but that's perfectly fine. Right. So this is an example. This is a statement of the mean value theorem, and then here is an example, right, where we find the instantaneous rate of change perfectly matching the average rate of change on a given interval. So, all right, great. Thank you so much for watching. Hope that was helpful.